Welcome to Mathematical Meditations. I'm your host, Ted Z. A couple of videos ago, I did one on Lagrange's identity. This one, you may recall. It was called Lagrange's identity and Cauchy-Schwarz inequality. Now, in that video, a viewer made a very interesting comment that this Lagrange's identity is a consequence of something in geometric algebras. So let's say G is a geometric algebra and we have two objects in G. We form the geometric algebra product like this. It's the scalar product, dot product of U times V, plus the wedge product of U times V, something like the cross product. Okay, so this is an interesting idea, and the viewer says that Lagrange's identity comes from looking at the norm of this geometric algebra product. Now, I don't really know anything about geometric algebras, but I did read an article by E.T. Jaynes, a funny personality from mathematics and physics. And he was writing about some work done by a guy named Histhenes. Now, Histhenes is one of these great minds of geometric algebra. Now, E.T. Jaynes objected to all this stuff with the remark, how can you add a scalar to a vector? You see here, this is a scalar and this is a vector product, right? So yeah, it seems to make no sense. However, if you think a bit further and we look at the case of quaternions, your typical quaternion is like A plus BI plus CJ plus DK. And this is the vector part, and this is actually just a scalar. So it is possible to have a scalar plus a vector, and it makes perfect sense for quaternions. And here, of course, these are IJK, the Hamilton imaginaries. So I had this idea based on that interesting remark of the viewer in that video, which you should go back and look at. I'll leave a link to it in the description box. It made me think that maybe I can prove this Lagrange's identity for the case n is 4 using quaternions, because quaternions are sort of like a geometric algebra. So that's what I'm going to try to do here in this video today. Let's start by reviewing how to multiply quaternions. P and Q are quaternions. There's 4 components. There's this scalar part here, a normal real number, then these imaginaries, IJK. And we can multiply them just plain old term by term, but we have to be careful. First thing we have to remember is I squared is J squared is K squared equals -1. And then if we need it, IJK is also -1. However, unlike complex numbers, Hamilton's imaginaries IJK are non-commutative. So here's a little trick on how to remember it. So if you go counterclockwise, all right, that's the normal direction. That's positive. So I times J is K. So let's see, I times J is K. But the other way around, J times I, well, if you go in this direction, that's negative. So J times I is minus K. So they're non-commutative. Let's draw this neatly like that. Likewise, IK is J is IK. Well, actually, I times K should be minus J because I'm going in this direction. I times J is K. J times K is I. J times K is I. K times J is minus I. K times I, all right, that's the counterclockwise direction, so that's J. But I times K will be minus J. While we're at it, let's define the norm squared of a quaternion. That's just this. You can guess that. It's just like vectors. In fact, if you define P conjugate, all right, P conjugate is when we replace I, J, K by the negatives, minus I, minus J, minus K, and then P conjugate, that's the same as the norm squared of P. Now, the first thing that Hamilton did, this is an interesting story, after he discovered quaternions in that famous eureka moment, the first thing he did was prove something called the law of the moduli. Law of the moduli, at least that's what he called it. So PQ, the norm squared of the product PQ, that's the norm squared of P times the norm of Q, norm squared of Q. Now this thing here, the law of the moduli, we're going to take this for granted. Hamilton already did the groundwork. He proved this. And this is what's going to enable us to prove Lagrange's identity in the case of quaternions. N is 4. 1, 2, 3, 4. Okay, let's go ahead and multiply two quaternions and see what happens. P times Q is, A1, A2, A3, A4 times B1, B2. Okay, and I'm going to do term-wise multiplications, and I have to keep in mind, you know, this thing here, I, J, K. All right, let's never forget this, and this is how they're going to be multiplied. So I'm going to do the term-by-term calculations quickly. You can do it yourself as an exercise. It's very fun to do. All right, so I'm going to do them one at a time here. First, the A1 multiplied by all of this stuff, A1 times B1, A1 times B2, and so on. Okay, that wasn't so hard because A1 is a scalar and it didn't change anything. So I'm done with A1. This is done. Now A2, A2I, well, this has an I, so when I multiply, I'm going to have to use my little triangle here to reason through that. So I'm going to do all of that, but I recommend you do it also by yourself. All right, so that's the next row here. And notice my scalar term is here, minus A2, B2. That's because I times I is minus 1. So that's where this minus comes from. Very nice. Okay, so we did this here. Now the next one, A3J. And I get this, and notice I have two minus signs. Just like the previous row here, there was two minus signs here, there's two minus signs here. There should be two minus signs in the next and the one after. All right, so I've done this one. Okay, now there's one more to do. And there we go, and it's two minus signs. Oh, there should be two. Yeah, okay, this is a plus. All right, yeah, there isn't another one after. It's just old dyslexic me talking. So, okay, this is all of them. And now I can rearrange it. I'll take all the scalars, like this one is scalar, this one scalar, this scalar. And then I'll take all of the i's. All right, so where's the i's? This one, this one, this one, and this one. And I'll join all those things together and write it all neatly. All right, that's the first line. That's all the scalar stuff. Now let's take the I component. I get this for the I component. And now let's do the J part of it. I get this and one more, the K component. All right, very nice. And looking this over, it doesn't look all that great because here I was hoping to get A1, B1 plus A2, B2 plus A3, B3 plus A4 B4. I was hoping to get something like this. That's sigma AI BI, and that's part of Lagrange's inequality. And here, it doesn't, this works out good. I get terms AIBJ minus AJBI, where I is less than J. But okay, that works. That's good. But this one is not of the same form like this. So it doesn't quite work. And yeah, I can derive Lagrange's identity from this, but it's going to be a real nightmare of algebra. So I was hoping that quaternions would help and make the algebra more elegant, not more complicated. However, all is not lost. Let's think of, I thought about this. Let's think about this. There's a minus, minus, minus. Some are minus, some are plus. Maybe there's a way to define P and Q a little bit differently so that I get this and I get this. Well, it's back to the drawing board. I'll take my quaternion P to be the same like before, but I'll change Q. So what I did here is my new Q is the conjugate of the old Q. See, there's all minuses in front of the vector part. And then I'm going to repeat the same calculation for P times Q. I recommend you do it. I'm just going to write the result down because it's a lot of writing. And I get this, and this is really good. So up here, this is sigma AI BI. So remember, sometimes I'm using IJ as indices. Okay, so don't get it confused with the imaginaries. Now, over here, mostly this is okay. This is AI BJ minus AJ BI with I less than J. There's an exception to it over here, but it won't matter because in the end everything will get squared. So this is looking really good. And what we're going to do now is find the norm square of this product, okay, which isn't too hard to find. I just square every one of these things, these components, and the ijk's go away. So this is the first thing, and this is exactly what I have. I equals 1 to 4. This is exactly what I have in Lagrange's identity, so that's a very good start. Next piece of the norm is like this. I square this coefficient in front of the I, then continue. Like this. Okay, so I'm going to call this part here star star. Okay, we're going to evaluate star star. So this bit, the first line that we already know is a piece of our Lagrange identity. But here, well, we have to think about this. All right, so I'm going to look at it this way. This is it's like A, big A, and this is big B. And we want to square these things. Well, A plus B squared, that's A squared plus B squared plus 2AB. And we can call this here the cross terms. Cross term. And there's going to be a lot of these cross terms. But first, let's compute this for star star. And let's add it all up together. So, okay, I computed all of these A squared plus B squareds for each one of these and added it all up together. But this is exactly sigma I less than J AI BJ minus AJ BI all squared. And this one here, it doesn't matter that it's backwards because of the square here. It makes no difference. All right, that's very good. Now we have to add these cross terms. Cross terms. And let's just hope that these cross terms are all 0, yeah? Okay, the cross terms aren't a big deal. We just multiply here this A times this B, okay? And then so on and add it all up together. So it's going to be 2 times the product of these things pairwise and adding them all up. All right, that's the first one done here. Let's do the second one here, like so, and one more, like this, and then close the bracket. There's this 2 out there in front. Okay, well, what I'm going to do here is multiply everything out and reorder. So I'm going to reorder everything in kind of an ascending order, both numerically and lexically, and that'll help me to identify terms that will cancel out. So I'm going to multiply like this times this, this times this, and so on. All right, that's the first line expanded. All right, second line, one more, like this, and close the bracket. Now the fun begins. We'll look for things that cancel out. I could see right away this guy and this guy goes away. Here's another one, this one and this one. Aha, this one and this one. Here's another one, this and this goes away. Oh, this one and this one. Let's see, there's more. There's more, hang on. This one and this one, that goes away too. And so the result of this cross terms is a big fat 0. Okay, so all the cross terms go away. All we have left is this stuff here. Amazing. So all this cross terms goes to 0, and all we have left is this. Well, very interesting. So what we have then is the following. Yeah, sum of AI, BI from 1 to 4 all squared. Yeah, and now, okay, those other terms like this, AIBJ minus AJBI all squared. Very good. But now we use the law of the moduli. And this is equal to, sorry, that's squared, P squared Q squared. Okay. But this is quite simple. This here is A0 plus A0 squared plus A1 squared plus A2 squared plus A, like this. Who starts counting from 0? I have to remember I'm not a computer scientist. All right, next. Like this. Okay, but we can now combine everything together. This all squared plus this, and no cross terms, and this equals sigma like this, and here sigma I is 1 to 4 bi all squared like this, each term squared like this. Well, there you have it. This is Lagrange identity for n equals 4. So it's a particular case. But the interesting thing about it is that we used quaternions to prove it. It's lengthy algebra, but it's quite interesting and kind of logical. Maybe you should go through it. It's very fun. Okay, that was very interesting. I thank that viewer for writing that very insightful comment that sent me off into the weeds with quaternions. And I will see you next time with more fascinating mathematical meditations.